In this video, we will discuss second order differential equations, part 2, unit 1. General form of the second order linear equations with constant coefficients is as shown here: a into d2y over dx square plus b into dy by dx plus c into y is equal to f of x. Note that the right hand side is a function of x only and not a function of x and y. Here a, b and c are constant coefficients. If the right hand side of the above equation is 0, then the equation is said to be the homogeneous form of the given differential equation. Thus, the homogeneous equation corresponding to the above equation is as shown here. This fx has been replaced by 0 to make it homogeneous. Let us discuss a term called auxiliary equations. We will introduce these operators. Capital D is equal to d over dx and d square is equal to d2 over dx square. So wherever we find these, we will replace them by the new symbols d square and d. For example, the given equation is this in its homogeneous form, or we may write the above equation as this. The last equation is a quadratic equation in D and has two roots d1 and d2 and is called an auxiliary equation. These roots will determine the solution of the homogeneous equation as follows. A. If d1 and d2 are real and different, then the solution of the homogeneous equation is this: y equal to a into x to the power d1 and plus b into x to the power d2. B. If d1 and d2 are imaginary, then d1 will be the sum of a real part and an imaginary part. Say d1 is equal to p plus iq. Since the imaginary roots occur in pairs, d2 will be p minus iq. Then the solution of the homogeneous equation will be y is equal to e to the power px into a sin qx plus b cos qx. C. If the roots d1 and d2 are real and equal, say d1 is equal to d2 is equal to p, then the solution will be as shown here: y is equal to e to the power px into ax plus b. This is the solution when d1 is equal to d2 and each is equal to p. Here we will solve example 1 of this unit. Solve d2y over dx square plus 2 dy by dx plus 5y is equal to 0. This is a second order differential equation with constant coefficients. It is in homogeneous form because the RHS of this equation is 0. The corresponding auxiliary equation is d square plus 2d plus 5 is equal to 0. The roots of this equation are d1 is equal to minus 2 plus 4 minus 20 square root divided by 2, which becomes this. Therefore d2 will be this because the imaginary roots, they occur in pairs. For the two imaginary roots found here, the solution of the given equation is as shown here: e to the power x into a sin 2x plus b cos 2x. Complementary functions and particular integrals. Let us consider the definitions of these two terms. Consider the equation a into d2y over dx square plus b into dy by dx plus c into y is equal to f of x. This equation is second order linear differential equation with constant coefficients. As seen previously, its corresponding homogeneous equation is this. That is, this replaced with 0. The solution of the homogeneous differential equation has a special name. It is called complementary function. So please, what is complementary function? It is the solution of the homogeneous equation corresponding to the given second order differential equation with constant coefficients. General or complete solution of the given differential equation, this consists of two parts. Complementary function, that is the solution of the corresponding homogeneous equation, this, and another solution called a particular integral, which is explained below. We rewrite the given equation using the operators capital D equal to dy by dx and d square, capital D square equal to d2y over dx square. This you have noted before also. Thus the given equation becomes this, or y becomes 1 divided by ad square plus bd plus c operating on fx, or y is equal to 1 over pd f of x, where pd is equal to ad square plus bd plus c. Now we follow the following procedure. Case 1. If fx is polynomial, operate on it with pd. Note that d during operation means differentiate and 1 over d means integrate. Use polynomial expansion of pd to the power minus 1 where necessary. Case 2. If fx is the product of a polynomial and e to the power kx, then take out e to the power kx and operate on the balance of the function using 1 over p d plus k. If the balance of the function is just a constant, then operate on the constant with 1 over p of k. However, should this lead to infinity in the expression, then operate on the constant as you would do on a polynomial. Case 3. Case 3. If fx involves cosine px or sine px, then replace cosine px by real part of e to the power minus px and sine px by the imaginary part of e to the power minus px. Re stands for real part and Im stands for the imaginary part. We will take up examples to illustrate these three cases in our next lecture. Thank you.